Hello everyone. Today on the IncQuery Labs Academy we will have a presentation by Peter Lunk on the model transformation debugger in VIATRA.
So hello everyone, my name is Peter Lunk and I will be conducting a presentation about debugging event-driven model transformations using the new developed features of VIATRA version 1.5. About myself, I have a master's degree in software engineering and I work as a software engineer at IncQuery Labs. And I'm also a commentator of the VIATRA project. So, what? So, yes. So about the presentation. At first, I'm going to talk about model transformation in general, to provide a little bit of context for this presentation. Afterwards, I'm going to talk about debugging model transformations in VIATRA. And finally, the last part of the presentation will be a live feature demonstration about the newly developed feature of the debugger itself. So firstly, model transformations in VIATRA. First, I'd like to provide a little bit of context about how model transformations are developed and basically what are model transformations themselves. One of the most important workflows built around model transformations is the model-driven software development workflow. Basically, you can imagine this workflow as a magic black box that incorporates all the related information about certain phases of software development, for example, like requirements, structural information, behavior information, implementation, and finally, by some sort of magic, it generates source code and test cases. However, in reality, it's quite complicated because these frameworks typically consist of many specialized sub-meta models that contain the specific information associated with a step in the typical software development workflow. These meta-model instances are maintained by a series of model transformations. And finally, based on the information collected in these meta-models, via code generator, source and test cases are generated. So one of the many reasons model transformation should be used is synchronizing these models. However, there are other auxiliary reasons why they should be utilized as well. For example, on-the-fly model validation, view model generation, for example, if we want to display specific data associated with these models. And also the code generation itself is a model transformation. So now that we know where model transformations are used and what they are, we should look at their internal structure and what they are on the inside. So typically model transformations are considered as programs which take a source model based on a source meta model and produce a target model based on a target meta model. On the inside, model transformations comprise of a number of model transformation rules. These model transformation rules typically consist of a left-hand side or rule precondition and the right-hand side or rule action. Basically, the rule preconditions define when the given rule should be executed and the actions define what should be executed. So basically, model transformation definitions contain a number of model transformation rules. However, in runtime, when an instance of a model transformation is running, the model transformation rules are represented as a set of rule activations. So basically, if you take an example that a model transformation rule precondition matches like 4 elements, 4 rule activations are created in the process and are executed eventually. So yes, exactly, rule activation contains, for example, if element A matches the precondition, it contains the action that needs to be taken, the explicit action that needs to be taken for element A. So apart from the actual structure of model transformation, it is quite important how model transformation activations are executed. This is often referred as the model transformation lifecycle. In this slide, I'd like to differentiate 2 main aspects of model transformation execution. One of them is batch execution, and one of them is a live execution. Typically, batch executions are explicitly controlled model transformations, meaning that the user defines that certain activations are executed at certain points in the software. So basically, we define explicitly when certain activations are executed. In an event-driven case, activations are executed in reaction to changes in the source meta model. For example, if so one of the rules is triggered and an activation is produced, then in a live environment, the activation is executed as soon as the model changes are applied. What I'm getting, so basically, the point of this slide is to point out that so various model transformation types contain various debugging properties. So basically, the more simpler batch transformations are easier to debug than the more complicated event-driven live model transformations. So because event-driven model transformations are more complicated, I'd like to continue the presentation. So I'd like to show you how event-driven model transformations work and how they should be debugged. And to this, I'm going to introduce a very simple example, which is based on the VIATRA CPS example we found in this technique. So basically, it's responsible for describing cyber physical systems. To achieve this, it utilizes three different meta models. First of them is the CPS model, which enables the user to describe cyber physical systems. Yes, so basically a number of hosts, applications, and state machines that are responsible for describing the behavior of the applications themselves. After the CPS model is complete, the CPS model can be extended with certain deployment information, and this is contained by the deployment model. Finally, the trace model is responsible for providing tracing information between the original CPS elements and the newly created deployment model elements. This structure is maintained by an event-driven model-to-model transformation. And finally, based on the deployment model, by a model-to-text transformation, C++ code is generated. However, in this case, this transformation is not explicitly important, so I'm going to concentrate on the model-to-model transformation that maintains the structure between the three meta models. Secondly, I'd like to show you the example transformation, which consists of two rules, which are quite simple, actually. First of them is the host rule, which is responsible for transforming host instances into deployment host instances, basically following this pattern. If a host instance is detected, which doesn't have any trace objects associated with it, then a deployment host object is created and a trace relation between them is set. The rule is similar in case of applications. If an application instance is detected, then a deployment application instance is created and the trace relation is set between them. Also note that if an application instance is referred by a host instance by an application reference, the deployment host associated with the host instance will also refer the appropriate deployment application as well. Implementation-wise, these rules, the rule preconditions are implemented as VIATRA queries, and the actions associated with the rules are implemented as Java or extend code as per by using the VIATRA transformation framework. About the execution of the model transformation, I'd like to show you this quite complex figure. So initially, we have a CPS model instance, we have trace model instance, and deployment model instance, all of them are empty. We also have the model transformation, which is initialized over this structure. the preconditions are implemented as VIATRA queries, and the model transformation agenda contains the previously mentioned application and host rules. If we change the input CPS method with CPS model instance, the changes are detected by the precondition queries, and according to these query result changes, the agenda, so activations of the application and host rules are added to the agenda. Firstly, because the host rule has a higher priority than the application rule, the deployment host element is transformed. Then after that, the appropriate deployment application element is transformed as well, and the trace model is also set. After this, these instances are removed from the agenda. If the input CPS model is extended further, then similar to the previous case, then activation is added to the agenda, and the models are updated in a similar fashion. So the next part, I'd like to talk about the challenges of event-driven model transformation development, specifically concentrating on how to debug event-driven transformations. So yes, we have this structure, and we have a source model, a model transformation, and a target model. The source model contains a fairly complicated structure. I wouldn't like to elaborate it. Just that it's a fairly complicated meta model and a typically large model. And usually, when we're developing model transformation, we are testing this model transformation using various test models. And the way we are detecting errors in the model transformation code is that an element is missing from the target model, and we have no idea what exactly caused the problem. So basically, in this case, there are three things that can go wrong. Firstly, our preconditions are erroneous, and also our action code could contain some bugs that so our action code could contain some bugs, and also there could be some problems regarding the rule priorities defined in our model transformation, meaning that the model transformation lifecycle could cause some errors as well. Firstly, a traditional approach will be to use the Java-based debug tooling of Eclipse, or any environment we're using to develop our transformations. However, it's not very convenient to use the conventional Java debugging tools for debugging model transformations, because typically debugging the precondition patterns is quite difficult using the standard Java debugger, as these precondition patterns are defined in a declarative domain-specific language. And the code generated based on these patterns can be quite complicated and hard to understand if someone has never actually seen it before. It's also quite inconvenient to debug the actions using the standard Java debugger, because using standard line breakpoints to debug actions is pretty inconvenient, because one needs to navigate to the exact activation which is important in the context of debugging, and it's quite hard to achieve by using traditional conditional breakpoints and typical line breakpoints. It's also similar with the lifecycle problems, because we need to be able to explicitly observe the internal structure of the model transformation agenda, and without any explicitly developed user interface elements which summarize the contents of the model transformation agenda, these informations can be quite overwhelming as well. One of the other options is using the VIATRA query results view, which is available since VIATRA version 1.4. It specializes in debugging VIATRA queries, which in this case are rule preconditions. It provides an abstract view of the internal structure of these queries and allows the user to browse the query results in a convenient and easy to understand way. So yes, basically I just need to image about the query results view, how the pattern results can be observed in this case. So our other debugging aspects in this case are, have I skipped one? Yes, I skipped one, sorry. So apart from debugging transformation preconditions, we could also use some tooling help with debugging transformation rule actions as well. So as I mentioned before, it could be quite helpful if the user could explicitly select which activation's execution should we stop the model transformation. So yes. So at which activation should the debugger stop the model transformation? And this could be achieved by a set of model transformation specific breakpoints. It will also be helpful if the model transformation debugger or any debugger application that is used for model transformation could display both the source and the target model at the same time. So because this way the user could observe the differences between the model instances. This way it could help detecting patterns that could cause any further errors in the code. Finally, debugging the model transformation lifecycle. To achieve this, the model transformation developer needs to observe the internal structure of the model transformation. And this way, as I mentioned before, the model transformation agenda should be displayed, and it's also beneficial for the model transformation debugger to be able to manipulate the state of the agenda as well. Meaning this that during runtime the transformation debugger, the developer could change the priorities of certain rule activations and specify which rule activations should be executed next. This way, elusive errors could be reproduced much easier. Yes. The next part, I would like to talk about the debugger itself, how its main architecture and what features it comes. Is that typo? No, there isn't. So about the debugger itself, as I mentioned before, it allows the user to observe VIATRA model transformations. It displays the agenda state and also displays the associated instance models associated with the model transformations in a side-by-side view. So it could be compared with each other. It also enables the user to manipulate the execution of model transformations. This can be done either by defining specific model transformation scope breakpoints, and also manually override the execution sequence of the individual activations. And this includes the regular Java debug actions that could be, for example, like stepping, continuing, or terminating the transformation under debugging. The debugger itself it relies highly on the Eclipse debugger framework. It reuses some of its UI elements, for example, debug view, variables view, breakpoints view, and the breakpoint implementations and serialization as well. Supports remote debugging of model transformations, meaning that model transformations running in remote JVM instances can be debugged as well. So in order to introduce a model transformation debugger, we needed to define some, so we need to redefine some standard debugging concepts. For example, we needed to, so in our case, activations are equivalent to lines of code in a standard Java or any other conventional language. Meaning that in our case, activations are treated as atomic elements, the debugger. We also need to redefine debugger actions because in our case, stepping, continuing, and terminating is quite different from the original meaning of these actions. And in our case, stepping fires the actual activations and actual activation instance, and after firing the actual activation, it stops the execution of the model transformation again. In case of continue, model activations are fired until the next breakpoint is reached, and in case of terminate, all breakpoints are disabled. The transformation is continued, and the model transformation debugger tooling is disconnected from the transformation under debugging. One of the actions we need to define specifically for model transformations is being able to manually override the execution of the execution sequence of the model transformation. As I've already mentioned before, this allows the user to explicitly select which activation should be executed next. We need to introduce various kinds of breakpoints. Firstly, we've introduced rule breakpoints, which define. So basically, rule breakpoints match any activation of a certain rule. So, for example, if an activation of a certain rule is about to be executed, then the transformation is stopped, and the user can define whether they should step or continue the transformation. These breakpoints can be defined in an offline manner, meaning that the debugger tooling doesn't need to be connected to any actually running model transformation, because these breakpoints can be persisted through actual debugging sessions. Another breakpoint type is activation breakpoints, which identifies any single activation of a model transformation. Naturally, these kind of breakpoints cannot be resisted, as they require runtime information about the activation they are associated with. And finally, a third type of breakpoints are conditional breakpoints. They specify global conditions that should apply to the instance models of the model transformation. They are implemented as VIATRA query patterns. They can be persisted as well between model transformation debugging sessions. But during definition and runtime, the metamodels associated with the model transformation need to be on the class path as yes, because during execution the VIATRA query framework, runtime framework needs this information. So, architectural overview about the debugger itself. It consists of two main components, a runtime component and a tooling component. The runtime component connects to the VIATRA transformation. It allows the user to manipulate and observe the transformation, then sends the debug information to the tooling side via a communication agent. The tooling side then displays this information. The user can select whether the transformation should continue or terminate or just step. Then the selected command is sent back to the debugger agent, which then allows the transformation to continue according to the selected command. So yes, as I mentioned before. In this figure, I'd like to show you how attaching a debugger agent to a model transformation can alter its execution. The example will be similar as the one seen before. However, in this case, a model transformation debugger agent is attached to it, and It's responsible for controlling the transformation and also provides information about its state. And as you can see, it contains a breakpoint that stops the execution every time an activation of the host rule is about to be executed. So in our case, a host instance and an application instance is related to the source model. Rule activations are added to the agenda. And in this case, as the host activation is about to be fired, the model transformation, the debugger agent stops the execution of the model transformation and waits for the user to select what should happen next. If a continue action appears, the debugger agent allows the model transformation to continue, and according to this, the model transformation is executed similarly to the previous example. So that was the regular part of the presentation. The next one will be a short live feature demonstration. I hope so. Yes. So. So the Eclipse instance should be shared right now. Is it shared? Can you see the Eclipse? Okay. So here's our host Eclipse instance. It has VIATRA transformation framework, VIATRA queries, and the VIATRA transformation debugger framework installed in it. We have an example just for this feature demonstration. It's based on the VIATRA CPS example. It contains a simplified version of the event-driven transformation specified there. Only in this case, the model transformation to the model transformation we attach a transformation debugger agent, which can be found here. So if we execute this model transformation, which will be run in an external in a separate Eclipse instance and resulting in a separate JVM. Via this action, we can start the event-driven transformation on a dummy model instance. As you can see here, the event-driven transformation is running, and at this point, the transformation is waiting for the tooling side of the application to connect to it. And if we switch back to the tooling side, we can define VIATRA transformation remote debugging sessions, which allow us to connect to already running transformation debugger agents. In this case, our debugger endpoint, which we have just started. So if we press debug, we are connected to the model transformation instance. So in this debug view, we can see which rule activation is about to be executed next. In our case, it's a host rule. In the transformation browser view, we can browse the agenda of the model transformation. Here we can see that there are a number of host rules which could be executed in this step, and the rule which is about to be executed next is displayed by using this red square. And also the transformation browser view allows us to observe the agenda of the model transformation via following two different semantics. Basically, we could either order the activations via their model transformation rule, in which case which is application rules and host rules. We could also order them, which could be executed. I mean, meaning that these rule activations are all of them have the highest priority at this point, so they could be executed anytime. So they could be executed because they don't have any other rule dependencies, which should be executed before them. And these application rules could not be because the respective host rules should be rule instances should be executed before them. So at the current point, the transformation is stopped before executing this host rule. If we, for example, select an application rule and we add a activation breakpoint to it, which is added to the breakpoints view, and let's disable this rule breakpoint. If we press continue, the transformation is stopped exactly at that activation, which we wanted to observe for any kind of reason. Yes, at this point we can observe the input and the output model instances as well. In our case, the CPS model contains a number of different host types, application types, with their respective application instances and host instances. Based on this, a deployment model instance is created. And as you can see, there is a properties view support for this model instance viewer as well, so we can observe the individual sub-properties of these elements as well. So we have a lot of time left. We could also add conditional and rule breakpoints as well to our model transformation. So adding a rule breakpoint basically looks like this. You should just enter in an identifier which should match the desired rule. In our case, rule. And if any application rule activation is about to be fired, then the model transformation will be halted. Yes, it's also possible to explicitly set the next rule activation to be executed. This can be done by selecting this button, and it sets the next executable transformation as the desired activation. Yes. Yes, I've forgotten about conditional breakpoints. Yes, so basically we can define VIATRA query patterns in these conditional breakpoints associated with the model instances if they are present in our workspace. So let's say we want to import the CPS model. We want to write a little test pattern for it. No, I just changed my mind. We want to use the deployment model. Yes, it would be better to demonstrate the capabilities of this. So we want to write a pattern that stops the execution of the model transformation every time a new deployment application is added, for example. So if we define a very simple pattern for that, and it's really simple, so just shift column. Nope. Okay, if we define this pattern, yep. Yes. Yes, using conditional breakpoints requires the runtime side to have the certain VIATRA tooling instances to be initiated, and in our case we haven't done this because I've forgotten about it. Yes. So if we open any component that utilizes the VIATRA tooling, and the required classes should be loaded, and we can successfully add the event model transformation breakpoint. Yes. I'm sorry about that. I've forgotten that this constraint exists. Let's reload the model. Yes. Oh, yes. It's already charging.
Oh, sorry.
So we check if the model transformation is actually running. Yes, it's running. We connect to it, and we just try to add a conditional breakpoint, and let's hope that this time it will work. Yes, it works. Yeah. So in this case, if a new deployment application instance is added to the deployment model, the model transformation execution will be halted, hopefully. Yes, it is. Yes, it has halted. As you can see, the original one of the original 4 application rule activations have been executed, and a deployment application has been added to the deployment model, which triggered the conditional breakpoint, and that caused the model transformation execution to stop. So yes, basically that's all I had in mind regarding the main functions of the model transformation debugger, and I'd like to continue the presentation part because I have one slide left. There are future features which are planned to be added to the model transformation debugger. Yes. Okay. We're planning to expand the current feature list via adding a model transformation profiler, implement a so-called time-traveling debugger, which allows the user to step backwards in the model transformation, not only forwards. And we'd also like to add a transformation trace logger, which can be used for static analysis of model transformations. We're also planning on improving the current user experience because it can be quite confusing sometimes. We'd like a closer integration with the Eclipse Java debugger. We want to launch model transformations in debug mode similar to launching an Eclipse application. Only in this case, we want to launch a model transformation instance with a debugger attached to it. And we'd also like to refine the current custom debugger views as the model instance browser or the model transformation browser, and enable them to have any more refined features as well. So basically, that was it. Thank you for your attention. So if you have any questions, you can ask them now.
Question. If you create a conditional breakpoint, the pattern that has multiple parameters, can you view the value of the parameters?
No, at this point you can't. But actually, conditional breakpoints work in the following way. So if the match set of the conditional breakpoints pattern changes, then the conditional breakpoint will enter a so-called dirty state, which will cause it to stop the execution of the model transformation. And at the current point, we cannot. We haven't implemented this feature yet, but it's a good feature request because the breakpoints view has a support for it allows us to display additional information about breakpoints in a similar to somewhat the properties view support, but it's not yet implemented.
But you could add constant literals to the pattern definition itself for the original request right now.
Yes.
Is it possible to use the traditional Java debugger and the new VIATRA?
Yes, it is. Yes, it is. It's not the. So the question was that if it's possible to mix the traditional Java debugger and the new VIATRA-based debugger. It is possible. So basically, the VIATRA debugger just stops the execution of the thread that runs the model transformation. And as we have navigated to the exact activation that we want to debug, we can use the debugger, the standard Java debugger, to debug the action code of the given activation. So at first we need to use the VIATRA debugger to reach that activation, and then the Java debugger to use that. But there is no explicit tool integration for this, so it's quite confusing, and it's a really advanced use case. But as I have mentioned on the previous, okay, so it changed directions somehow. So as I mentioned before on the previous slide, so yes, one of our goals is to have a close integration with the Eclipse Java debugger, which could abolish this issue, because we could add custom breakpoints to the Java debugger. So basically, we extend it with our special model transformation breakpoints, and this way, this extended Java debugger could be used for navigating to a certain activation, and based on that, regular line breakpoints could be used.
Okay, so we have a question from a viewer. István Rat asked, could someone build a transformation profiler on top of this framework? If yes, how? We already know it's planned, but how would you do that?
Quite easily. I didn't want to dwell into the architectural grids of the debugger, but it's based on a generic adapter framework, which could be used to insert any type of functionality into a VIATRA EVM, event-driven virtual machine based program. So it would be quite easy to develop a model transformation profiler with the given tooling we have and the generic tooling we have developed for the debugger. So basically, that's it.
Okay, if we have no more questions, then thank you for the presentation.